Good morning. Today I have zircon and zirconia. They're special refractories. They have limited use, um, but they have some very good properties, and they're also, especially zirconia, more expensive. So we'll do zircon first, and we'll go over the raw materials, look at the phase diagrams, how this material is made, what the final microstructure looks like, and a couple properties. So the raw material is zircon sand, CrSiO4. It has a density of 4.5 grams per cubic centimeter, and it's about 67% zirconia and about 33% silica. So this raw material comes with additional minerals, impurities, ilmenite, FeTiO3, rutyl TiO2, and there's always some hafnium in with zirconium. So there's a hafnium silicate, HFSiO4. So there's a small amount of hafnium that's in solid solution with the zircon. So here's some raw materials, one from Australia, India, Nigeria, South Africa, and America. So this is ZrO2 plus, let's say, a trace amount of HFO2. They're all about 65% except this one, which is a little bit lower. And if you look at the silica contents, this should be about 34, 35%. This one's a little higher, almost 40%. And the impurities are typically Fe2O3, Al2O3, TiO2, and P2O5. So this one from Nigeria probably has some silica present as quartz on their raw material, because the impurity level isn't any higher than the other ones. So about 65% ZrO2 and about 35% SiO2 with these impurities. One of the problems with zircon, it's only stable to 1540 degrees C. So if you go to temperatures higher than 1540 degrees C, it'll decompose to zirconia, ZrO2, and silica SiO2, and the silica will be in the cristobalite form. So this is the simple reaction. Zircon decomposes to zirconia and silica. So if we look at the phase diagram for ZrO2, SiO2, this is 100% zirconia on the left-hand side. On the right-hand side, it's 100% silica. There's only one compound here, this vertical line, that's zircon ZrSiO4. And the temperature is 1400 up to 2800 degrees C. So if you look at this compound zircon, as you heat it up, to the left here, the phase field is zircon plus zirconia. To the right, it's zircon plus silica. But this dotted line is 1540 degrees C. You cross that temperature, you decompose into zirconia and silica. And then the first liquid, zirconia plus liquid, appears at some more or less than 1700 degrees C. So zircon is stable to 1540 degrees C. It decomposes to zirconia and silica at higher temperatures. So there's a couple things you can do here to make this a useful refractory. You can add alumina, Al2O3. So now you have zircon plus alumina. If you heat it to temperatures higher than 1540 degrees C, you're going to end up with zirconia, ZrO2, and then our alumina silicate compound mullite, 3Al2O3, 2SiO2. So you can add enough alumina to react with the silica that forms and end up with zirconia and mullite. Or another possibility, when zircon decomposes at 1540 degrees C, you can add MgO. So now you have zircon plus MgO, and that forms zirconia plus phosphorite, this magnesium silicate, which is a high temperature material. So you add enough MgO to react with the free silica to form this material phosphorite. So those are our two possibilities to make a material that's going to be more useful at higher temperatures. Of course, you can always use zircon at temperatures lower than 1540 degrees C, and it'd be just fine. So you start out with zircon sands for processing. And again, typically they're crushed, screened, and mixed into their desired particle size distribution. And this is a dry press operation with an organic binder. And it has to be fired at a temperature less than 1540 degrees C. So it's typically fired from 1300 to about 1500 degrees C. So the microstructure is simply polycrystalline zircon and porosity. So this would have no alumina or magnesia additions. So the larger crystals here are about 100 microns. So you can see the larger aggregates and then the finer matrix, and the black areas are the pores that are present. This one looks like it's a pretty porous material. So if you add alumina to zircon and you add it in excess, more alumina than needed to react with the free silica, you'll have an alumina bonded by zirconium mullite and maybe a small amount of glass present. And if you add excess MgO, more MgO than needed to react with the silica, you can have MgO bonded by phosphorite plus some MgO stabilized zirconia. And we'll talk about stabilizing zirconia in a few minutes when we talk about zirconia. You have to stabilize it because there's phase transformations. So these refractories are going to have a matrix of zirconia and mullite, or phosphorite and zirconia. So zircon has a pretty low thermal expansion, 4.5 times 10 to the minus 6. That's comparable to materials like silicon carbide and silicon nitride. And keep in mind that MgO is about 13.5 times 10 to the minus 6. So it's got a pretty low thermal expansion. It also has a high thermal conductivity. So that combination of low expansion, high thermal conductivity basically minimizes thermal stresses. So it has good thermal shock resistance, and it has very good corrosion resistance. It's poorly wet by molten glass and molten metals. So any material that's not wet by a slag or a glass or metal is going to have good corrosion resistance, because it really eliminates or slows down the chemical reactions at the hot phase. So it has good thermal shock resistance, good corrosion resistance, but at 1540 it decomposes. So here's a zircon, another zircon. This is one that has excess alumina. Here's a zircon alumina refractory, and this is a very dense zircon. So some of these are used in glass tanks in contact with glass, and some of these are used for special applications like nozzles and tubes for metal casting. So the density in grams per cubic centimeter, these are about 3.75. This one's lower because it has alumina additions. And then this one is high, 4.3, because it has very low, it's processed at very low porosity, 1%. So these other three are typical 18, 17, and 19% porosity. Has excellent cold crushing strengths. These are all over 10,000. This one's over 50,000 because of the very low porosity. Pores are defects, they lower the strength, but with this low porosity, the strength goes up. They measure RULs on these. They're all around 1650, 1700. And then the thermal expansion, that's this percent at 1,000 degrees C. These are all pretty low, 0.4, 0.4, and 0.4. And then this one's a little higher because of the alumina additions. So the first two and the third are zircon, about 65% ZrO2, 34% SiO2. And you can see this one has a significant amount of alumina added. So about 69% alumina. So the zircon content is the zirconia content is about 19% and the silica is about 10%. So those are some typical zircon refractories. Zirconia will follow the same pattern here. The raw materials, the phase diagrams, how these materials are made, and what their microstructures and properties look like. So the raw material for zirconia is badiolite. It's in the monoclinic form, and that's the material is rare, so it's not a viable source of zirconia. Sri Lanka and Canada are the two sources. So the ZrO2 content is, in this case, is 99 and this is 98%. So these are pretty high purity materials, but they're very scarce. They're rare materials. And SiO2, Fe2O3, CaO, TiO2, and then the hafnium oxide and FeO are the typical impurities. So how do you make zirconia? You have to start out with zircon sand. So that's the major source of zirconia. So ZrSiO4 is the zircon sand. And then you have to process that zircon sand to make ZrO2 zirconia. So there's three different ways of producing ZrO2 from zircon. There's a fusion reaction. There's a reaction with alkali or alkaline earths. And then there's a plasma arc melting technique. So in the fusion reduction, you're simply mixing zircon sand with a carbon source. In this case, I have coke here. This is the way iron and other metals are made. You simply reduce the iron oxide with a carbon source to form the metal. But in this case, you're forming zircon and SiO and CO. So you're mixing the zircon with coke. You fuse it in an electric furnace at 2800 degrees C, and it follows this reaction here. Zircon plus carbon yields zirconia plus SiO gas plus CO gas. That SiO gas will react with oxygen to form SiO2 silica. So you can also react it with an alkali or an alkaline earth. So here's an example of a reaction with lime, CaO, and this one is reacted at 1600 degrees C, and you're going to end up with zirconia and a calcium silicate. So CaO plus the zircon sand forms zirconia plus this calcium silicate, Ca2SiO4. So then you have to take this calcium silicate and leach it with an acid, and that leaves fine zirconia powder. And then in the melting technique, the plasma arc melting, that dissociates zircon into zirconia and silica. And this is usually taking place at around 1750 degrees C, and certainly above 1540 degrees C, where zircon decomposes. You have a molten material, it solidifies in an amorphous silicate glass. So the temperature is high enough to melt the silica. Silica melts a little over 1700 degrees C. So you're going to end up with a silicate glass, and in that silicate glass, you're going to have zirconia crystals. So then you have to dissolve the silicate glass, and you can use a caustic soda. So you dissolve the amorphous silicate glass, and you end up with fine particles of zirconia and probably some silica impurities. So this is the phase diagram for ZrO2, pressure versus temperature. This horizontal line is 1 atmosphere. So there are some displacive transformations, monoclinic to tetragonal and tetragonal to cubic. That's heating. On cooling, it's the reverse, cubic to tetragonal to monoclinic. So here's a region of liquid. Here's the cubic phase of zirconia. Here's the tetragonal phase. And then over here is the monoclinic phase. So these phase transformations at 1 atmosphere are displacive. So as soon as you go from cubic to tetragonal, that's a displacive transformation, and from tetragonal to monoclinic. And you can also, if you have a cubic phase, it may be metastable, depending on how you process it, to room temperature. And the tetragonal phase can also be metastable down to room temperature. So there's a monoclinic, a tetragonal, and a cubic form. The transition from each crystal structure is a displacive transformation, which creates some problems, some serious problems during the processing. And you also have the cubic phase. So these are the phase transformations. So the top is heating. So between 20 and 1100 degrees C, you're going to have monoclinic zirconia. And as soon as you get above about 1170 degrees C, there's going to be a displacive transformation to tetragonal. And then you get above 2370 degrees C, it's going to be another displacive transformation to cubic. And then above 2680 degrees C, it's going to be liquid. So on cooling, you're going to form the cubic phase. And then when you get down to about 1100 degrees C, the tetragonal is going to convert to monoclinic. So heating, you go from monoclinic to tetragonal to cubic, and on cooling, you go from cubic to tetragonal to monoclinic. So zirconia melts at about 2710 degrees C, and this polymorphic displacive phase transformation, monoclinic to tetragonal, takes place in this temperature range, 1000 to about 1200 degrees C. It's not an exact temperature. It's a function of the microstructure, the grain size, but it's a displacive transformation. So when you go from monoclinic to tetragonal, there's a substantial volume decrease, 9% volume decrease. So the tetragonal crystal is denser than the monoclinic. So going through this displacive transformation is a destructive process. The mechanical properties are really degraded. So it's going to create a severely microcracked structure. So you really can't cycle zirconia through this monoclinic to tetragonal phase transformation without really creating a severely microcracked microstructure. And you're going to lose a great deal of your mechanical strength. So you have to do something with zirconia. You have to alloy it with another chemical. So special alloying, how you process it, and how you develop a microstructure, these are all important in order to make a functional refractory. So this is the expansion. This is volume expansion versus temperature. So as you heat the material, you're in the monoclinic phase region. So you have your normal thermal expansion behavior. But then when you get about 1100 degrees C, you have this phase transformation from monoclinic to tetragonal. And so there's a volume decrease because you're going from a low density monoclinic material to a high density tetragonal material. So there's this volume decrease. And then when that displacive transformation is complete, you start a normal thermal expansion behavior again. So this displacive transformation that takes place there is very disruptive to the microstructure. So this is linear expansion versus temperature. There's another example. And the solid line is the first cycle. So you heat it up, normal linear type thermal expansion. And in this case, you reach, I guess, 1179 degrees C. You have the transformation, the volume decrease, continued heating. You start following normal thermal expansion behavior. So when you cool it down at about 1048, you go back from tetragonal to monoclinic. You have a volume increase. At this point, this decrease and this increase really disrupts the microstructure. It's severely microcracked. And then when the transformation is complete, when you have all monoclinic, it follows normal behavior, normal thermal expansion behavior. But you see there's an offset here about 0.3%. That's because of all the microcracks that formed. The material is not going to close back. There's going to be open microcracks. So there's a permanent volume change, which it shows up here. And the dotted line is cycle 2. It's basically the same as cycle 1, but because it's already severely microcracked, it tends to come back to its original size in the second cycle. So there's various things you can do with zirconia. You have to stabilize it. So you have to stabilize zirconia with other chemicals, other additives that form solid solutions. So one possibility is adding lime. So CaO stabilizes the cubic form all the way down to low temperatures. Remember, the cubic form was the highest temperature form. So this lime addition makes a useful refractory. It suppresses the tetragonal to monoclinic transformation. So it keeps everything in the cubic phase field. So if you add 5% CaO, the melting point is still really high, 2600 degrees C. If you add a little bit more, up to 7 weight percent CaO, the melting point is still high, 2500 degrees C. So besides CaO, there's other stabilizing agents, yttrium oxide, Y2O3, and magnesium oxide, MgO. So there's 3 possibilities, 3 different additives that you can use to stabilize zirconia in this cubic form. So if you look at the phase diagram, this is on the left-hand side, 100% zirconia. And on the right-hand side, it goes up to about 50% CaO or lime. That's in mole percent. On the bottom here, on the top, it's in weight percent CaO. It goes up to about, say, 30% CaO. So what you do is you add enough CaO to get over here into this cubic 0.2 phase field. So you see, as you heat it up, you just have cubic 0.2 up until these high temperatures here. This is the solidus curve. So you want to keep it in cubic. If you're over here, you have monoclinic and cubic. Well, that transforms to tetragonal. This one transforms to tetragonal plus some cubic. So that area of the phase diagram you want to avoid. Add enough CaO to get into the cubic zirconia phase field. So here's monoclinic zirconia. Its density is 5.83 grams per cubic centimeter. Tetragonal is denser. It goes up to 6.1 grams per cubic centimeter. And then the cubic form is about the same density as tetragonal, 6.09. So you're stabilizing it in the cubic form. If you add Y2O3, this is the phase diagram for zirconia, Y2O3, and this is in mole percent. So this is 100% CrO2. This is 100% Y2O3. So this large phase field here, right there, is all cubic. To the left of that, you have cubic and tetragonal and cubic and monoclinic. So you want to avoid this part of the phase diagram right near CrO2 by adding enough Y2O3 to get into this cubic phase field. And again, the solidus curve here is above 2260 degrees C. So it's a high temperature material. And then the other additive, MgO, this is this ZrO2 MgO phase diagram, 100% ZrO2 on the left and about 50% MgO on the right. That's in mole percent. On the top here, we have the weight percent going from 0 to, looks like about 24%. So here's your cubic phase field, a cubic zirconia in this system. Below that, you have tetragonal zirconia and monoclinic zirconia. But this looks like it's going to transform as you decrease the temperature. But this cubic form basically remains metastable all the way down to room temperature. So the kinetics are not just exactly right for the transformation. So if you use this cubic zirconia formed with the MgO additive, you can use it for long times below 1400 degrees C, but eventually you're going to have the transformation take place to tetragonal monoclinic. So it'll remain metastable, but if you're using it at high temperatures, like 1400 degrees C, it's going to eventually form tetragonal and monoclinic. Well, you simply start out with zirconia. You add a stabilizer, whether it's CaO, MgO, or Y2O3. And these are crushed, screened, and mixed. These materials are usually made into pretty dense form, so the particle packing has to be adjusted correctly. And there's some type of organic binder added. So these are made into maybe slide gate plates, nozzles, tubes, or even refractory brick shapes. So they can be extruded. They can be isostatic pressed to achieve a high density, or they can be dry pressed. And then they're fired at pretty high temperatures, 1750 to 2000 degrees C. So there's three types of zirconia refractories, and they're all going to have different microstructures. So how you process these materials, you're going to obtain different microstructures. So there's a CZS, a PSE, and a TZP. So CZS is cubic, fully stabilized zirconia. So you add enough of the stabilizer to be fully cubic. PSZ is partially stabilized zirconia. So you don't add enough of the stabilizer to completely get it in cubic form. And then TZP, you have very minor amounts of the stabilizer. So you're making a material that's going to be entirely in the tetragonal zirconia phase. So these are all polycrystalline materials. So CZS is cubic fully stabilized zirconia. So you're stabilizing it in the cubic form with, let's say, lime you have to add at least 15 mole percent, or yttria, you have to add about 8 mole percent. So these are the minimum requirements of additives to get it in a cubic form. Center it on a high temperature, 1750 to 2000 degrees C, and you're going to end up with a polycrystalline material, all cubic 0.2. And PSE, the partially stabilized zirconia, you're going to partially stabilize the cubic form. Now you're going to add lime to about 6.3 to 9.3 mole percent, or MgO 7.2 to 10.2 mole percent. So you're not adding enough of these stabilizers to completely form the cubic phase. So you don't have enough stabilizer to make 100% cubic crystals. These are centered typically 1700 to 1800 degrees C. At those temperatures, you have a homogeneous cubic solid solution. Crystal size is about 100 microns. And then you have to heat treat that material, and you heat treat it at a lower temperature than the sintering temperature, maybe 1200 to 1500 degrees C. So within the cubic crystals, you're going to precipitate the tetragonal crystals because you don't have enough stabilizer, either CaO or MgO, to completely stabilize the cubic form. So now you have a microstructure with tetragonal precipitates inside cubic crystals. So fine tetragonal precipitates are uniformly distributed within the large cubic crystals. If, depending on how you process this, and we'll go over that in a few minutes, you can have tetragonal crystals. They can also transform, the displays of transformation to monoclinic crystals. So you might have fine tetragonal precipitates. If they transform, you're going to have fine monoclinic precipitates, which are the transformed tetragonal precipitates. So you're either going to have tetragonal precipitates or monoclinic precipitates in these cubic crystals. And then TZP is tetragonal zirconia polycrystals. So you're going to have a minor amount of additions, maybe a few mole percent, Y2O3. Cerium oxide is another stabilizer. That one takes a little bit more, 12 to 15 mole percent. So you center these at high temperatures up to 2000 degrees C. And you're going to have a microstructure of very fine crystal, submicron crystal sizes. And you're going to end up with all polycrystalline tetragonal ZrO2. There's going to be no monoclinic or no cubic. So CZS, cubic fully stabilized zirconia. Here's an example of a microstructure that's stabilized with Y2O3. That's all cubic. And the larger crystals here on the order of a couple microns. So it's a polycrystalline material, all cubic zirconia. This is another microstructure of CZS, fully stabilized in the cubic form. Now this one has an MgO stabilizer. You can see again, the individual crystals and their grain boundaries. These crystals, the larger ones, are about 5 microns. And then if you have a partially stabilized zirconia, this one has an MgO stabilizer. You can make out the crystals. You can see these black dots are internal porosity. You can make out the grain boundaries. So the larger crystals are about 100 microns. So they're partially stabilized. And then if you go up to much higher magnification, this is the same material. You can see the tetragonal precipitates in the cubic matrix. So these light gray crystals are tetragonal precipitates, in this case, in a cubic matrix. So the precipitates are only on the order of 0.2 microns, so they're very small. So that's a partially stabilized zirconia with tetragonal precipitates in a cubic matrix. You can also have monoclinic precipitates in the cubic matrix if you allow the transformation to take place. And I can go over that in a few minutes, why you have either tetragonal or monoclinic precipitates. And this is a TZP microstructure. That's tetragonal zirconia polycrystals. This is a yttria stabilized material, a very small yttria content. So it's a fine crystal size. The biggest crystals are about a half micron in size. So these are fully in the tetragonal form. And here's another example of tetragonal zirconia polycrystals, TZP. Also a small amount of Y2O3 stabilizer. And the larger crystals here are about 5 microns. So this microstructure has been etched. You can clearly see the crystals and the grain boundaries. So for CZS, which is again, fully stabilized cubic zirconia, this material has high thermal expansion. It has low thermal conductivity. So its thermal shock resistance is not going to be very good. It has poor thermal shock resistance. And it always seems like every refractory has a trade-off in properties: poor thermal shock resistance, extremely good corrosion resistance. So molten metals, molten slags really don't wet zirconia very well. So there's a unique property in this material, the stabilized zirconia. It has high electrical conductivity. So it's ionic conductivity. It's not electronic, so it's not conductivity due to electrons. It's due to ions moving. You can actually use this material as a high temperature heating element. So what happens when you stabilize the zirconia? You're adding CaO to this material, ZrO2. So the Ca ion goes on a Zr ion site. So Ca goes on Zr site. So the notation here is the Ca ion is sitting on a Zr site. Then this oxygen is going to sit on one of these oxygen sites, one of these 2 oxygen sites. So you have an oxygen on an oxygen site, but there's only 1 oxygen here, there's 2 here. So you're going to create a vacant oxygen site. So every time you add CaO on one compound, 1 Ca, 1 O, to ZrO2, the Ca goes on a Zr site, the oxygen goes on an oxygen site, and you create 1 vacancy. So when you add 10 mol% or whatever of CaO to ZrO2, you're going to create a lot of oxygen vacancies. So you're going to have a large oxygen vacancy concentration. And these vacancies start to order on planes when there's a large concentration of vacancies. So the electrical conductivity is due to oxygen ions moving through the vacant site. So the oxygen is jumping from one vacant site to another, and it's O minus 2. So you're having a negatively charged ion moving through the structure. So that gives rise to electrical conductivity. And that's going to take place at very high temperatures. So that ionic conductivity is useful if you want to use a cubic zirconia as a heating element. The partially stabilized zirconia, I mentioned you can either have tetragonal precipitates or monoclinic precipitates. So you can have these tetragonal precipitates in a cubic matrix that's stabilized, or you can have monoclinic particles that precipitate in the cubic matrix. So what determines whether they're tetragonal or monoclinic is their particle size. So depending on how you heat treat these, how you grow these precipitates, If the precipitate is less than this critical size, DC is a critical diameter. Um, if it's less than that, the tetragonal form tends to be stable. It's constrained by the matrix from transforming. If the particles are larger than this critical size, the transformation takes place and you have monoclinic precipitates. And that's a spontaneous transformation upon cooling. This critical size is about 0.2 microns. So depending on how you heat treat this after the firing process and the size of the crystals you grow, you'll either have tetragonal precipitates or monoclinic precipitates. So if you end up with tetragonal precipitates, you're going to have very high strength, high fracture toughness material. And the matrix, the cubic stabilized matrix, constrains the transformation from taking place because there's a volume expansion when you go from tetragonal to monoclinic. So the matrix constrains the tetragonal particles as tetragonal in the tetragonal form. So why is this material so strong and so tough? Well, the toughening or strengthening mechanism is the displacive transformation from tetragonal to monoclinic. So when a crack moves through a material during the fracture process, it has a frontal process zone. That's an area at the crack tip that's highly stressed. It also has a process zone in the wake of the crack behind the tip. But in this case, the frontal process zone is the most important. So at the tip of the crack, it's highly stressed. There's a frontal process zone. That stress field provides enough energy to force this transformation from tetragonal to monoclinic. So the stress field, when that transformation takes place, it absorbs energy, and because of the volume expansion from tetragonal to monoclinic, it puts a compressive stress in this frontal process zone, and it basically stops the crack from moving. So this toughening or strengthening mechanism is only effective at low temperatures because at high temperatures, the tetragonal form is stable. It's not going to transform to the monoclinic phase. So this material has really good mechanical properties at room temperature or temperatures slightly higher than room temperature. But when you get up to high temperatures, the transformation doesn't take place. So it's not really useful as a high temperature refractory. So this is what happens. That's some schematic diagram showing what happens in partially stabilized zirconia. So this is a crack moving from left to right through this material. The circles are the precipitates. So the black circle is monoclinic, the open circle is tetragonal. So around this crack tip is this highly stressed area, the frontal process zone. So right in the vicinity of the crack tip, these black circles are the transformed monoclinic phase. Away from the process zone, they're still tetragonal, the open circles. So the transformation here, the volume increase, basically puts a compressive stress on this crack and stops it. This one, they just added some secondary particles, and there's probably thermal expansion mismatches. So they're just there to create additional microcracks that absorb energy. So one way you make a thermally shock resistant material is you develop microcracks in the vicinity of the cracks that develop during thermal shock, and those microcracks absorb energy and take it away from the basically take the energy away from the growing crack. So thermal shock resistant materials or refractories are generally materials that are highly microcracked. So if you have the monoclinic precipitates, they've transformed, they've created microcracks. So those cracks lower the strength, but you still have high fracture toughness because those micro cracks absorb energy. So the tougher the material is, the more resistant it is to crack growth. So the toughening mechanism here, instead of the compressive stress that develops at the crack tip, you now have micro crack extension. You create fracture surface energy, you create fracture surface areas, and that requires energy, so the energy is absorbed in these micro cracks. So when you cool this material down, you go through the tetragonal to monoclinic transformation, you're going to create micro cracks. Again, cracks present are going to lower the strength, but it's still going to be a tough material because you still have to extend those cracks during crack growth. So you have controlled crack growth under thermal stresses, and you have material with good thermal shock resistance. So you're going to have maybe 20 to 40% of the monoclinic zirconia and maybe 60 to 80% still in the cubic form, the stabilized form. So this is what happens in this material with the monoclinic zirconia. So some schematic diagrams. Here's a crack moving from left to right. This is your frontal process zone where the stresses are very high. You have these micro cracks, and they're going to continue to grow in size and absorb energy. That's an ideal case, a uniform distribution of microcracks all growing. But more realistic, these microcracks link up and form larger cracks. So that's the difference between the two partially stabilized zirconias, one with the tetragonal phase, one with the monoclinic phase. And then this material, TZP, tetragonal zirconia, has very little stabilizer. So the idea here is to retain all of the tetragonal zirconia in the metastable form all the way down to room temperature. So you have a very fine grain size tetragonal crystals, and the constraint, what stops the transformation, isn't the constraint is imposed by grains that are in contact with each other. So you're using these very fine tetragonal crystals to constrain themselves. And they're metastable all the way down to room temperature. Unfortunately, the toughening mechanism, the transformation that takes place, is only effective at high temperatures because, again, at high temperatures, the tetragonal phase is stable and it's not going to transform to monoclinic. So this has really high strength and high fracture toughness, so very good mechanical properties at low temperatures, like room temperature. But when you get up to high temperatures, the transformation won't take place. So it's not really that useful either as a high temperature refractory. So this TZP, the tetragonal zirconia polycrystals, they have high fracture strength and high fracture toughness. And again, the toughening mechanism in the frontal process zone is this transformation, the displacive transformation from tetragonal to monoclinic. The volume expansion puts a compressive stress on the crack tip, stops the crack from moving. Also, there's energy absorption that takes place during that transformation. So when a crack moves through this material, you're going to have 100% transformation. So all the tetragonal crystals in the process zone are going to convert to monoclinic. So here's a CZS, a PSZ, and a TZP. So this is fully stabilized zirconia, this is partially stabilized, and this is unstabilized. These are useful refractories. They're used in a lot of special applications like tubes and nozzles for controlling metal flow. These can be used at lower temperatures for wear resistance. They're very hard materials. So the stabilized zirconia has a density of about 4.9 grams per cubic centimeter. because of the lower amount of stabilizers here. These are really dense materials, about 6 grams per cubic centimeter. This one is made with about 13% porosity, typical of refractory materials. These are made very dense. They're actually high performance technical ceramics. So the cold crushing strength for this first material is high, over 12,000 psi, but these, because of the low porosity or basically no porosity, this one's almost 300,000 psi, and this one's well over 300,000 psi. So these are very strong, tough materials because of the transformation that's taking place in these materials, toughening them. These aren't really refractory materials at high temperatures, but this one is because it's fully stabilized. So it has a high RUL, 1700 degrees C. So it doesn't start really deforming till high temperatures. And these thermal expansions are not low, 0.8, 1, and 1.1 that's percent at 1,000 degrees C. So this one is about 95% of ZrO2. And the manufacturer kept it a secret what the stabilizer is, but it's going to be MgO, CaO, or Y2O3. And then these have some stabilizer in them, and it happens to be Y2O3. So the balance is going to be ZrO2. And here's some other materials. The first 4 are partially stabilized zirconia, and the last one is tetragonal zirconia. And these are the compositions, different mole percents of MgO and CaO or a combination. This is the tetragonal content. This one, because it's all tetragonal, is 97%. K1C is the fracture toughness. So fracture toughness is a material's ability to resist crack growth. So the higher the toughness value, the more ductile the material is, basically. So this is in KSI inches, square root of inches. And 8.7, 8.1. These are high values. These are 5.1 and 6.2. They're still high values for ceramics, and this is 5.8. And the strength is in KSI. So these are all high strength materials. And the grain size, these are all like 60 to 80. And then this one has to be very fine in order to make the tetragonal zirconia stable at low temperature. So it's only 1. So there's a temperature limitation for partially stabilized zirconia or tetragonal zirconia. So above 1150, the tetragonal phase is stable. It's in equilibrium. It's not going to transform to monoclinic. Some of it can also be metastable down to lower temperatures. So there's no strengthening and toughening above 1150 degrees C. And as you increase the temperature, there's a progressive reduction in the strength and fracture toughness. So this is MOR in megapascals, and in parentheses, it's MOR or strength in KSI. So the strength versus temperature. This is a tetragonal zirconia. This is a partially stabilized zirconia. The strength is falling off because you're losing the toughening mechanisms. So the strength falls off with temperature. And then this is fracture toughness in megapascal square root of meters or KSI square root of inches. And this goes from 2 to 12, and that's in MPa square root of meters. And also in parentheses is KSI square root of inches. It's a little bit lower when you do the conversion than in the megapascal square root of meters. So toughness versus temperature. And it falls off on this yttria, slightly yttria stabilized material, which is tetragonal in the tetragonal form. So a toughness of 8 is really high for a ceramic or refractory material. A glass, which is very brittle, has very little resistance to crack growth, is going to be about 0.5 MPa square meters. A refractory material like a fire clay or high alumina, for example, is only going to be about 1. So it has very low fracture toughness. And a metal like steel is going to be way off the chart. It's going to be like 200 megapascals square meters. So the metal is very ductile, so it's going to resist fracture. So typically, glass and refractories are way down here, around 1 or less. Having a material around 8 is a pretty good value for the toughness. And again, steel is way off the chart at 200 or more. So the strength and toughness are going to fall off with temperature for these partially stabilized or unstabilized materials. So that's the last slide I have on zircon and zirconia. Again, if you have any questions, just let me know. And again, thank you for listening today. And today's Wednesday, so I'll see you on Monday. Have a good weekend.